Okay. So we're very happy to have Leah McAllister here from Cornell.
Thanks, John. And thanks to the organizers for giving me the opportunity to speak here. It's, as always, a great privilege to be able to address all of you. So let me begin with a brief summary of the main points of the talk. And if you catch only this slide, that'll cover everything. So we give explicit constructions of n=1 supersymmetric AdS4 vacua along lines proposed long ago by KKLT. And we do so in orientifolds of Calabi-Yau hypersurfaces in toric varieties. We find explicit quantized fluxes for which the flux superpotential is exponentially small and the string coupling is polynomially small. The non-perturbative superpotential arises from rigid prime toric divisors with constant Pfaffian prefactors. All the tadpoles are canceled and all the moduli are stabilized. We explicitly include the leading alpha prime corrections, which in this setting are world-shade instantons contributing to the Kähler potential. And to do this work, we relied on a bunch of new tools for computing Gopukum-Ravafe invariants, for constructing orientifolds, for uplifting to F-theory, and then for enumerating Euclidean D3 branes and M5 branes in orientifolds and in F-theory. And all of these things at large Picard number. We have not yet considered arranging for a suitable warp throat for uplifting to de Sitter, so this talk is exclusively about supersymmetric AdS4. Of course, de Sitter is an interesting question for the future. So here are my collaborators, Mehmet Demirtas, Manki Kim, Jakob Moritz, and Andres Reyes-Tascon. And we've relied heavily also on a bunch of works in progress with those authors in various combinations, as well as Naomi Gendler, Ben Heidenreich, Tom Rodelius, and Mike Stillman. The work that I'm talking about today will show up imminently. We're just finishing off a few more examples beyond the ones that I'll show you today. So the broader goal, just to give a little bit of context for this work, is computation of the string landscape. What we'd really like to be able to do is to understand through enumeration what kinds of things are possible in quantum gravity. And we like to construct ensembles of vacua whose phenomenology we can study. So this is a specific example and a starting point toward more things. So here's the plan of the talk. First, I'll explain how we get an exponentially small flux superpotential along lines that we proposed in 2019. I'll then say how we get the non-perturbative superpotential from rigid divisors. We'll combine those things and get supersymmetric vacua, and then I'll talk about control of corrections in those vacua. So the KKLT recipe is extremely familiar, but the trouble is getting your hands on the right ingredients. So what we have to first do is establish that the superpotential takes the form proposed by KKLT, namely, it contains a flux superpotential that depends on the complex structure moduli Z and the axiodeleton tau, and it also contains a series of non-perturbative terms. Here I'm writing a sum over divisors D inside a Calabi-Yau, and exponentials of the complexified volumes TD of those divisors. The factor CD is the dual Coxeter number, so that'll be 6 for an SO8 stack of 7 branes, and it'll be 1 for Euclidean 3 branes. And then the prefactor AD of Z tau, well, is a Pfaffian, a one-loop Pfaffian that in general depends on the moduli as shown. Now, what we need to do is arrange that W0 is extremely small in the vacuum configuration, and also arrange that we find at least H11 non-perturbative terms, independent ones, whose Pfaffians are not 0. We're going to impose a stronger condition. We're going to impose that we find at least H11 non-zero Pfaffians that are pure numbers with no moduli dependence. And that will simplify things. So for the point of the flux superpotential, we use the mechanism that we've proposed. To get enough rigid divisors, we're going to look for rigid prime toric divisors, which are easy to analyze from toric data. And then finally, to ensure the Pfaffians are numbers, we're going to find a toric uplift to F-theory, compute the intermediate Jacobian data by stratification, and ensure that the intermediate Jacobian is trivial so that the Pfaffians are sections of the trivial bundle over the complex structure moduli space, and hence have no moduli dependence at all. Now, on the first point, let's start talking about the construction of small flux superpotentials. General statistical arguments suggest that small W0 should occur, but should do so exponentially rarely, and preferentially when the dimension of the moduli space is large. So the tools that I'll be describing do permit us some ability to explore such moduli spaces, but it's still the case that a brute force search is quite challenging. So it's going to be better to invent and apply a mechanism so we can get a little bit past the best previous record for W naught, which was around 10 to the minus 2. We'd like to press on to smaller and smaller W naught because it's a control parameter in the KKLT scenario. So the smaller, the better for some purposes. So now here's the mechanism. It's a racetrack mechanism. And in first reviewing the basic idea of a racetrack, this is quite an old idea. Suppose I have a superpotential generated by instantons for some complex field Z. And suppose the two most important terms have some prefactors n1 and 2, and exponents p1 and p2. The superpotential, of course, goes to 0 as z goes to infinity. But you can find its minimum value by solving the flatness condition, and you find it's some combination of the numbers n1 and 2, p1 and p2. But the racetrack observation is simply that if the two exponents p1 and p2 are quite close to each other but not exactly equal, and if the prefactors n1 and n2 are slightly hierarchical, why then the superpotential at the minimum is extremely small. Okay, this is a way of generating via the exponents showing up here. You put in polynomial-sized inputs, the p's and the n's, and you get an exponentially small w. Now, that's the intrinsic mechanism. Now, if you want to do this in string theory, we should really show that in a legitimate solution, first of all, the flux superpotential takes that form, and the exponents are close to each other, but not equal, and the prefactors are hierarchical. Then we'll have succeeded, we'll have shown that W naught is given by a formula like this and is exponentially small. So on point 1, we established a sufficient condition on the topological data. The sufficient condition essentially tells you that you want to arrange that the quantized fluxes give 0 contribution from the part of the prepotential that in terms of type 2a on the mirror manifold appears perturbative. The fluxes then give a contribution to the flux superpotential only through the part of the prepotential that's non-perturbative, coming from worldsheet instantons of type 2a on the mirror. And that's why it's all exponential. So we found a condition that can be fulfilled. And for point 2, we just found examples. So let me just show you an example. So here's one brief remark. If you analytically continue this mechanism, these constructions to the conifold, you find vacua where both W naught is small and you can have a warped conifold. So that's a nice thing to know about for some future work about uplifting, but that's not going to be relevant today. We won't be arranging for conifolds in the work I'm describing now. Okay, so here's an example of a flux superpotential in a Calabi threefold with H21 equals 5, H11 equals 81. We find these quantized fluxes. So there's some vectors of fluxes, very modest integers, such that a particular direction in the joint complex structure and axiodilaton moduli space is a perturbatively flat vacuum in the sense that I just described. So this is some rational ray along which the complex structure moduli and the axiodilaton are proportional in a particular fashion. All right, so that's some direction in the moduli space, and along that direction in the moduli space of this particular Calabi, the leading instantons have the Gopa-Gamaravafa invariants listed here. And the flux superpotential turns out to look like this. So the point is that the exponents are 3/8 and 5/12, and that prefactors are in fact hierarchical, one's 2 and one's 324. And when you solve, you find that the moduli are stabilized at G string 0.05 and W naught 10 to the minus 23. So this is certainly an exponentially small flux superpotential, so that's great. This is now an illustration of the mechanism at the level of the flux superpotential, but let's ask how we're going to make more of these things. So how do we actually manufacture small flux superpotentials? So you begin with an oriental fold of a Calabi. You compute the prepotential via mirror symmetry, and then what you should try and do is find some quantized fluxes that align with the GV invariance of the mirror, X tilde, to give a type 2A worldsheet instanton racetrack along some flat direction. And you better do so within the D3 brane tadpole. Now that third step is a search in a flux lattice, and the dimension of it is 2 times H21. And that's feasible for H21 less than about 5 on a laptop or maybe 7 on a cluster. And so we're going to have to work at pretty small H2, small dimensional complex structure moduli spaces. So whole context, where we're going to do all of this work in Calabi-Yau hypersurfaces, we'll work with mirror pairs in toric varieties obtained from triangulations of four-dimensional reflexive polytopes given to us by Kreutzer and Skarka. And this is certainly a large enough realm for an exploration of these possibilities, and we'll see there's a lot going on therein. All right, so suppose we're looking at four-dimensional polytope from the Kreutzer-Skarka list. What are we going to need to figure out in order to try to find a KKLT vacuum? At least these data. We'll need to find a triangulation, compute the intersection numbers of a Calabi-Yau threefold hypersurface in the toric variety, compute GV invariance, find an orientifold, uplift the orientifold, and then find divisors in F-theory supporting Euclidean M5 branes or in type 2b supporting Euclidean D3 branes. So how well can we do all of these things? Well, the first three things you can easily use CY tools to handle for anything in the Kreutzer-Skarka list. And I'm happy to say that now we also have the capability of doing the remaining things, not all the way up to 491, but up to, let's say, 100 without much trouble. So let me picture that for you on a Hodge numbers plot. So we're talking about the Hodge numbers of X, the threefold that we'll actually be working with rather than its mirror. In the green band at the bottom is where we can search for flux vacuum. It's where H21 is less than about 7. And the purple stripe vertically is where the GV invariance of the mirror can be computed using off-the-shelf software like Instanton. And if you look at where those things intersect, you see there's no points in there. So there basically aren't any polytopes, there aren't any Hodge pairs where those capabilities align. So we're going to have to do better. So first of all, we got better at computing GV invariants. Now we can compute them all the way up to 100 or something like that. And now there is an area of overlap between where we can compute and where we can search for flux vacua. It's this sweet spot here. But there's something to learn about that sweet spot, which is that H11 is relatively big. In fact, it's typically of order 100 in the examples where we can work on the complex structure moduli side and find flux vacuum. So we're going to have to do everything at large H11, the orientifolding, finding rigid divisors, uplifting, computing GV invariance, the whole works. In our examples, we don't find any particularly compelling geometries with H11 less than of order 30, and all of our best ones have H11 at least 51. Okay, so far we've talked about computational capabilities and about the flux superpotential, but we really want to get the non-perturbative terms. So what we're going to try and do is find at least H11 rigid prime toric divisors whose uplifts to divisors in F-theory have trivial intermediate Jacobian in an orientifold configuration where all the 7 branes lie in SO8 stacks, and so generate condensates. Now, just a reminder, what I mean by rigidity here is just that the vector of Hodge numbers of the uplifted divisor is 1, 0, 0, 0, and a smooth divisor with those properties, per the analysis of Witten 1996, contributes to the non-perturbative superpotential. If, moreover, one finds that H21 of the uplifted divisor is equal to 0, the intermediate Jacobian is trivial. And so the Pfaffian prefactor is a section of a trivial bundle over the F-theory complex structure moduli space, i.e. it's a complex number rather than a moduli-dependent function. And that is extremely valuable for ensuring that we're not going to suffer from unexpected zeros, that we could push to a point moduli space where the Pfaffians go to 0. They don't go to 0 because they're just numbers. All right, but to do this, we need to compute the Hodge numbers of divisors at large H11. And you can't do that, at least we can't envision doing that sort of by grinding it out. Instead, we had to obtain a combinatorial formula via stratification. Basically, we needed to do everything torically, and when you do that, you can obtain a closed form expression for these data. And with that in hand, we could carry out a search, and we found lots and lots of examples that fulfill these requirements. But now let's find supersymmetric vacua in them. So if I now list only the H11 leading divisors, this is the KKLT superpotential and the leading Kähler potential. V is just the volume of the threefold as a function of the complexified Kähler moduli Ti. And now the ADIs are some constants, and W naught is an exponentially small constant, like in the example 10 to the minus 23. All right, we're going to solve the F flatness conditions for the Kähler moduli to find a supersymmetric vacuum. And that's easy to do. If you remember the CIs, or the dual Coxeter numbers, you see rather quickly that the Kähler moduli will have volumes that are proportional to log of 1 over W naught, which is big, times a factor CI over 2 pi. And so that just means that the SO8 stack divisors have to be 6 times bigger than ED3 divisors in order for them all to be commensurate contributions at the F-flat configuration. All right, so this is the equation that we'd like to solve, but where in the Kähler cone is a point obeying this condition? So here's a picture, a two-dimensional slice, of course, of the Kähler cone of, for illustration purposes, a threefold H11 equals 491. And let's imagine that we start in the white circle off toward the left, and the SUSY vacuum is on the right. Somehow we need to make our way through all of the intervening phases, each chamber of which corresponds to a different triangulation, and make our way over to the supersymmetric vacuum, where all of the Kähler moduli are inside the Kähler cone. The Kähler parameters Ti are inside the Kähler cone. So to do that, we developed an algorithm that takes a bearing, finds the way to the supersymmetric vacuum, and just walks there through all the phases in between, and does so quite quickly. So that's good. We can find the vacua as well, but let's see if we should believe that we have control of the vacua. So that means we need to understand, do we understand the superpotential and the Kähler potential? The superpotential is pretty clear. We've ensured that the Pfaffians are non-zero numbers by very standard zero mode counting. And their numerical values have really small effects. So if you change them by a factor of 10,000 up or down, our vacua persist. So you would have to do something really extraordinary to get rid of the vacua by factors of 16 pi squared and the like in these Pfaffians. Even so, it would be wonderful to compute them directly. And one can show quite explicitly that all further instanton contributions to the superpotential are completely negligible. One can also check, since the string coupling is so small, that ED-1 contributions, which you could view if you like as contributions to the flux superpotential, are likewise safely negligible. So the superpotential is under very good control. We've established that it takes the KKLT form. How about the Kähler potential, though? The Einstein frame volumes are large. They go like log of 1 over W naught. But G string goes like 1 over log of 1 over W naught. It's small. And those factors, depending on W naught, cancel out in computing string frame volumes. So string frame volumes are actually order unity. And so you might panic and say, doesn't that mean it's impossible to control the alpha prime expansion? The good thing is we're at quite weak string coupling. And so the leading corrections that we need to know about are at string tree level, but to all orders in alpha prime. And those are not that hard to understand, in fact. We can write them in terms of an expression for the volume, like this. These are just the corrections inherited from n equals 2 supersymmetry. They include the famous BDHL perturbative correction, proportional to zeta of 3, and then an infinite series of worldsheet instanton corrections. What I've drawn here, or what I've shown you here, are both the potential, the expression for the volume, and also the expression for the corrected Kähler coordinates real of big Ti, in terms of the Kähler parameters, little ti. So the Kähler potential and the Kähler coordinates. And both of these receive a series of worldsheet instanton corrections. And here the n sub q's are the Gopukumar-Vafa invariants associated with curve classes q in the Mori cone of the threefold that we're studying. Now, can we control those sorts of instanton sums? Well, so let's define the quantity Cn, which is, for n a natural number and q a curve class, it's the GV invariant of n times the curve class times the exponential of the curve class times n dotted with the Kähler parameters. In other words, this is the size of the nth term in the worldsheet instanton expansion along a direction defined by the vector q. Well, we're under control, things are converging. As n goes to infinity, Cn goes to 0. And we're not just going to check that things converge, we're going to compute the contribution and incorporate it in our analysis. But we want to check, all right, do these worldsheet instanton sums in fact converge? So we just compute the GV invariance for small curves, small volume curves, and we check. So let me tell you about one example. Of the 175,772 smallest curves, almost all have 0 GV invariant, so they don't contribute anything. 25 have non-zero GV invariant. But then we cast a wider net, we looked bigger, we found lots more curves that had non-vanishing GV invariant. Fine, but most of those still have the property that if you look out along the associated ray, you don't find an infinite series of non-vanishing GV invariants, but after a finite distance, usually after one step, the GV invariants are 0 thenceforth. Along such rays, you don't have an infinite number of states to worry about, and those curves are safely collapsible. We do include them. They're very numerous. We include them, but they don't have a particularly dangerous effect. But that's not completely satisfying. We'd like to find some curves that have infinite series, or at least plausibly infinite series of growing GV invariants, and make sure that those are safe as well. So what we did is we kept searching outward in this example until we found 758 rays of curves that did have plausibly infinite series of non-zero GV invariants, which increase as the number k or n increases. Namely, as you go out along the ray, the GV invariants grow. So here's a plot of Cn.
Liam,
So
you have about 4 minutes left.
Got it, thanks.
That's up.
On the left, you see the log of this control parameter Cn versus n. First thing I'd like you to observe is these are all lines. And there's no extrapolation here. We are interpolating because little n is an integer. So we have to interpolate between, but there's no fit required or anything. These GV invariants really do come in extremely regular exponential growing progressions. So that's, I think, a rather beautiful structure. What you also notice, I hope, is that the slopes of all the curves, all those lines, are negative. The right-hand side is a histogram of the slopes of the curves on the left. And what you can see is, though we tried very, very hard to see if there were any dangerous curves whose associated slopes would be positive, that would mean that as you go toward higher and higher degrees, you get bigger and bigger contributions. We didn't find any. The histogram just completely drops off and doesn't reach 0. That means things are under exceptionally good control. In fact, the worst individual curve contribution is a contribution of order 10 to the minus 7, which of course is totally negligible here. So finally, before concluding, let me just show you one example, flash it up on one slide. So here's the example whose superpotential I've already shown you when giving an illustration. The polytope in question is shown here. So the vertices of the polytope, the columns, that matrix shown. In this geometry, there are 18 SO8 stacks and 66 Euclidean D3 branes wrapping rigid prime toric divisors. All of these have H21 of their uplift being 0, so they have constant Pfaffians. The charge in Fluxes is 71/2, and the D3 brane tadpole is 44. So there's 8 D3 branes and then 1/2 D3 brane that's stuck on an O7 plane stack. I show you here the GV invariance, the flux superpotential, the stabilization of the superpotential at around 10 to the minus 23. And in this geometry, we find a supersymmetric ADS4 vacuum where the string frame volume is 500, the Einstein frame volume is like 10,000 or something, and with vacuum energy 10 to the minus 63 in Planck units. Okay, so let me conclude, and then I can take questions. So we've given explicit constructions of supersymmetric ADS4 vacua in Calabi-Yau three-folds orientifolds with H21 up to 7 and H11 at least 51. The stabilization is at weak string coupling, large complex structure, large Einstein frame volume. These are very heavily tested. We judge them to be robust, but if you find further technical tests that you think might be worthwhile, we'd love to hear them. We're happy to poke at these examples further, and we'll be putting the data associated to them as supplemental material with our paper. So these are incarnations of the KKLT scenario, although they have some distinct features. And so our main finding is that supersymmetric KKLT vacua are in the landscape. One striking feature is that the mechanism that we used to get small W0 led to giant hierarchies, and that could be interesting for other purposes. Another relevant point about the way we carried our analysis is that the search is automated. And so rather than have to craft these one at a time, one paper at a time, large-scale studies are now possible, and we could generate families of supersymmetric KKLT vacua. An uplift is a question for the future. Thanks a lot.
All right, great. Thanks, Liam, for the very nice talk. Let's all thank Liam. We have time for, a few questions. I think Jim has his hand raised first.
If organizers are allowed to ask questions.
Beautiful
talk. No, I mean, this is an amazing standard you guys are setting for putting the pieces together at large topological numbers. My question was about this clever technique that you had about the trivial intermediate Jacobian giving rise to constant Pfaffians. So my question was going to be, what about the ones that don't have constant Pfaffians, because there could be other divisors. But in some sense, I think you were saying implicitly that all of those are subleading. Was there some sort of mechanism in homology that was guaranteeing that those were subleading?
Yeah, that's a great question. So one thing that we did, of course, is we made a cut, right? So we have all of Kreuzer-Skart to look at. And so if we found ones where a bunch of prime toric divisors had non-constant Pfaffians, we would just discard them. Now, I don't see a reason that you couldn't learn to live with non-constant Pfaffians, but we wanted to be completely clear for this first step. Okay, so I think a very natural subsequent work would be to analyze cases where there are plenty of non-constant Pfaffians. But now to your actual question. What we typically find in the good models is that there's a couple of divisors, a couple of prime toric divisors with H21 of the uplift not equal to 0. But the thing is, there are H11 plus 4 prime toric divisors. And typically some of the extra 4 are just a lot bigger, multiplicatively bigger, sometimes a large multiple bigger than the sort of basis ones. And so we can just find configurations where those ones whose Pfaffians we don't really know much about are exponentially negligible in comparison to the ones that we've retained.
Right, so they're sort of larger in homology in a sense, and that the constant Pfaffian ones are sort of small, and then you're adding them up to find the non-constant ones or something.
Yeah, but we're not saying that there's a mechanism that makes this always be true. What we're doing is we're filtering out ones that are definitely bulletproof by that standard.
That makes sense. Wonderful. Thank you. There are tons of other questions. I'll stop.
I think Ralph was no.
Hello, Lime. Nice talk. I was just having a question about the mass scales between the Kähler moduli you stabilized by 3-brane instantons and the lightest complex structure modulus. I thought they were of the same scale, so you seem to have resolved this problem. I didn't see it in your talk.
No, thank you. No, that's an excellent point. The cool thing is because the Pfaffians are all independent of the complex structure moduli, inclusion of non-perturbative terms in the superpotential that depend on the Kähler moduli doesn't shift the complex structure stabilization appreciably. So indeed, one direction, that perturbatively flat direction that you know well, is about the same mass scale as the Kähler moduli. But when we study the Kähler moduli potential, they're not, that particular guy doesn't care what's happening with the Kähler moduli. Now, had the Pfaffian, why did we go to this trouble of making the Pfaffians constant, right? You might say, oh, at a generic point in moduli space, they should be some numbers anyway, so it's probably fine. Well, a conspiracy theory would be that always that latest direction has a Pfaffian that does something bad as you try and stabilize. And so we just had to ensure that, no, it's a number, so nothing bad can happen as you try to stabilize.
So this is why you required this in the first
Yeah, because we didn't know which one that was going to be, and we wanted to make sure it was safe.
Yeah, thank you very much.
All right, I think Fernando.
Yes, a very nice talk, Liam. Enjoyed. Just well, following up on the Pfaffian story, I found surprising things. First, that you found all the Pfaffians to be different from 0, and then you found them to be constant. How generic is that? I mean, I think the natural thing would be non-constant, and some of them would be in 0. Eh?
Right. So one thing which is generic at large H11, which you can pretty easily see from the number of points in the dual polytope, is that a huge number of prime toric divisors are rigid. Huge number. Not always H11 or more, but always H11 maybe minus a handful or something like that. And the reason roughly is most of these divisors correspond to points inside 2 faces, because once you have a polytope with a ton of points, you got to start packing some of the points into a 2-face. And those things have a very hard time getting a Hodge vector in 3-fold terms other than 1, 0, 0. So those guys almost always help you out, and you just have to get a little bit more to be above H11, to be at or above H11. Now, the Pfaffians were all constant. That took a little bit more work, and I won't say we've explored the space of possibilities enough to quote statistics there, but that was not a very severe cut also in our analysis. So yeah, it seems to be feasible. One does typically find that 1 or 2 divisors have Hodge vector like 1, 0, 1 or 1, 0, 2. But we just had to arrange that those ones were the bigger ones that didn't matter.
Okay. And on the GV invariants, do you understand why they tend to vanish?
Oh yes, that's a long story that we do sort of understand, which I'd be delighted to explain. Roughly speaking, the cone, the Mori cone, has a really thin cone inside it, along which there are infinite series of GV invariants growing exponentially. And so correspondingly, if you were to try to collapse those curves, you'd bring down infinitely many states and you'd be in big trouble. And outside of that is like a very thick sheath around that cone, consisting of mostly curves that are completely collapsible. The GV invariant of the curve is 1, say, and of twice the curve is 0. And that basically corresponds to the possibility of making tons of different flops. And as you can, from the picture I showed of a cross-section of the Kähler cone, there's tons of different places to go. That's sort of related to the presence of what we call the nilpotent curves.
Okay, thank you.
Okay, so it looks like we're out of time for questions. So Severin, if you could bug Liam on Slack, and we'll move on to our next talk, which is